In this experiment, we're going to take a capacitor and we're going to charge it with different resistors here. And so as we do that, we're going to have this SparkView data logger as this voltmeter here. And that's going to show us the charging of the capacitor, which will give us the time constant. And so as we can graph the time constant and versus resistance, so resistance on the x-axis, time constant on the y-axis, that is, that'll give us a gradient of delta y and delta x, which will be tau, the time constant, over r, the resistance, which will give us the value of the capacitor. So it's just changing the resistor, and then we're measuring the voltage and then calculating the time constant from that. Just make sure that you have the resistor correct. So I would directly measure the resistor with the multimeter. So make sure it's set on ohms and have the red on the ohms and the black on the coms, or vice versa. And then I would also do a double check, use the color code chart. And this resistor here is green, blue, red. So green is 5, blue is 6, so that's 56, and the red is here, 2 zeros, because it's not 4, there's only 3. So we skip this one here, and so that's 5,600, and it's a gold over here, so that's a plus or minus 5%. We're going to do plus or minus 10% because some of the resistors we're going to take the largest error and some of them had 10. Okay. And this is just showing it in action. So we press this down and that will now charge the capacitor. And we're going to change the resistors here. So we have a resistor located down there. All right. And then you can see the curve will go up. And then once it evens out, it's reached full resistance. So it goes from 0 to whatever the voltage is on the battery or the power pack. And then we will let it go, and you can see it will slowly drop off. In order to make it drop, it's going to very slowly dissipate. So to make that quicker, we do this path here, so we can discharge it quickly, and that will allow us to hurry up and do more trials. That other resistor, that 220 ohms, we always put resistors in circuits so the load goes through the resistor and not through the wires and burns the wires. Okay, so that is just to quickly discharge it. So you can see from the SparkView here, we have the charging. So it's usually a nice little bit of a curve. This one's quite sudden. You can see this part here is when it's discharging. So we click the switch to make it discharge much, much quicker. There's a fault with this one because it doesn't reach 0. And so that circuit needs to be fixed and problem solved. But we're going to use it anyway to describe how to read it. Okay, so the first one is you go to the very highest voltage there. You can see it's 7.7 volts after 15.9598 seconds. Then we have to get a calculator out and work out what the time constant is. So 63% of that 7.75 is 4.88. And so then we drag down the cursor down to 4.88, and that'll give us a 15.35 seconds is the time for that. Now we have to work out when it starts. So it says 1.47, but let's pretend that's 0, and that starts at 15.16. And so the time it takes to go from 0 volts to 63% of 7.75 volts is 15.35 minus 15.16, so it's 0.19 seconds. That's the time constant. Okay, so now we have our raw data here. So we have all the resistors, and we did each one 3 times. And for each of those 15 data points, we had to do that. So that's quite a lot. We had to take 63% and then work out what the time difference from the start to that is. And that's where we get that raw data. So now I'm just making it a lot more prettier. I'm just going to bold everything, the headings that is. I've got to make sure I get my symbols in there. So insert symbols. I'm doing some various headings. I'm doing percent difference to see if there's any anomalous results. I'm also going to look at percent error. That's assuming that the capacitance, which is the gradient, is the true value, and doing a calculation from that. Okay, so I'm centered everything, wrapped it, just made it look nice. So just making the table look good like that. Okay, so the next thing I do there is the average. So if I'm going too fast, you can just slow down and see what things I've pressed on to get the average. And I just drag that down and it does the average for all of them, making sure also I do the correct sig figs. The next thing I'm doing is percent difference. So that is each value minus the average divided by the average. I don't like to do the absolute values. I prefer to leave it as is so I can see if the percent difference is increasing or decreasing, because you can pick up further systematic errors that way. And I've locked in one cell using those dollar signs. That can be quite useful as you drag across, if you want one value not to change as you drag across. Now I'm going to insert a scatter graph, and so make sure before you start you choose a graph that has lots of grid lines. I just copy and paste to get the labels on the axis. And when I insert the trend line, I made it to 0. I don't know if that's technically correct actually, but it is approaching 0, so that's my justification. It just makes it simpler because we're looking for the formula there of capacitance equals tau on R, so the gradient is the capacitance. And to do error bars, just the error bars that I've already predetermined from the uncertainty in the graph, just their fixed values of 10% and 0.01. Now that I have my equation of the line, I can do a percent error on that, because 470 microfarads is the capacitance it's meant to be, and we got 471 microfarads. And so that gives us a percentage error there. And we're now going to use that equation to work out as the true value, even though that is an experimental value, but we're going to call it a true value and do a percent error on that, and work out percent errors on the time constants that we've measured. That's just allows for further analysis. Okay, and we're done.